for normally hyperbolic invariant manifolds and applications to the Hamiltonian stability problem.
So I would like to start by thanking the organizers for the opportunity to be here. So this is a joint work with Rafael Darayave from Georgia Institute of Technology and Teresa from Universitat Politècnica de Catalunya. So this talk is more on conservative dynamics than on symplectic geometry. So, and I also want to say that it's a talk that I have given a couple of times this summer, so it's about to reach its expiration point. So I'm sorry if you have already heard a similar talk at the previous conference this summer. So because of the nature of this talk on more on the dynamics than it is on the geometry, so I'll start with some introduction on the main problem, and I'll give some background necessary to formulate some shadowing lemma for normally hyperbolic invariant manifolds. And then I will formulate a general diffusion type of result and some applications. So, the main problem that makes the subject of this talk is the Hamiltonian instability problem. So this is a problem that actually goes back to Poincaré, who considered the study of the nearly integrable Hamiltonian systems one of the most important problems of dynamics. And as a very concrete example to study, Arnold in 1964 proposed this type of Hamiltonian, which is consists of a rotator and a pendulum plus a small periodic coupling, which is of a very special type. So this is a two-parameter problem. One parameter accounts for the hyperbolicity of the system. The other one is an external perturbation applied to the system. And the question that Arnold was trying to answer by looking at the system is, if you apply a small perturbation of this type, whether it's possible to find a solution of the system for which the action variable of the rotator changes by some quantity independent of the size of the perturbation. So essentially, if you do not have the perturbation at all, your system is a product, so the action variable will be preserved. Then you apply a small perturbation and you're asking if for all sufficiently small perturbation, whether you are able to find solutions for which the actions changes by some quantity independent of the size of the perturbation. And for this type of system, Arnold proposed a mechanism of showing the existence of such orbits, existence of diffusing orbits. So just to make the system Hamiltonian, like an autonomous Hamiltonian, you do the standard trick. So you add an extra variable which is symplectically conjugate with the time. And then first you start to understand the geometry of the unperturbed system, and then you move on to the perturbed system. So for the unperturbed system, so when epsilon is equal to 0, you are able to identify four-dimensional normally hyperbolic invariant manifold. When you restrict to some energy level, you find a three-dimensional manifold which is foliated, which is filled by two-dimensional tori. And for each of the torus, so this is a representation of these three-dimensional normal hyperbolic invariant manifold, so it has stable and unstable directions. But if you look at each torus, the stable and unstable manifolds coincide. So if you're asking the question whether you are able to change your action variable for this system, the answer is of course not. So this is a product system. So if you stay on the normally hyperbolic, on the cylinder, you are just going to remain captured on the same torus for all time. Or if you want to follow one of these homoclinic orbits, which is created by the separatrix of the pendulum, you are going to fall back on the original torus. So when you do apply a small perturbation, the type of perturbation that Arnold designed, so as I pointed out, so this is not just any perturbation, so it's a carefully chosen one. So that carefully chosen perturbation does not affect any of the invariant tori, but what it does, it creates a splitting between the stable and unstable manifold. So you are going to be able to start with one torus, follow the unstable direction. The unstable manifold is going to cross the stable manifold of some nearby tori. So in this way you go on the stable manifold and you make some progress, you move to a nearby torus, and then you repeat this excursion, so you're able to create a chain of invariant tori, and then you use some sort of obstruction argument, which is very simple. It's points at topology to prove that they are actually true trajectories that follow this chain created by tori and their stable and unstable invariant manifold, and in this way you can create orbits for which the action variable changes order 1 with respect to the perturbation. So this is a very nice and very important mechanism of diffusion. However, the system that Arnold described is very special because the perturbation is very special. So the perturbation is not generic. So if you try to think about the same problem with a generic type of perturbation, then you encounter some obstacles. So first of all, you are not going to have that all tori are preserved anymore. So you have the KM phenomena that tells you that while most of the tori will survive the perturbation, you are going to also create some gaps between the invariant tori, and the size of the gaps is like order square root of epsilon with respect to the perturbation. However, the splitting created by the perturbation between the stable and unstable manifolds is only order epsilon. So the amount that you can move using the heteroclinic excursion is smaller than the gaps that are created. So then the geometric method to overcome the large gap problem is to look at the objects created by the perturbation inside this large gap. So you try to study what are other objects that you can use in a transition chain. So you have the KM tori, which are essentially deformations of the original tori from the integrable system. But then you try to link together some of the new objects created by the perturbation, and they can be like secondary tori, or another way to call them these elliptic islands, or lower dimensional tori and their hyperbolic invariant manifolds. So in this picture you have some hyperbolic periodic orbits and their stable and unstable manifolds. Or you can try to involve Aubry-Mather sets that exist in these gaps. So, so the answer essentially is, instead of transition chains consisting of invariant tori, you add in the transition chain this type of objects, and you are more or less able to replicate the Arnold's mechanism of diffusion. So the objective of this talk is really to achieve diffusion without transition chains. So we are not going to chase for invariant objects in the normally hyperbolic invariant manifolds that we can use for the transition chains. But instead, we want to develop some specialized shadowing lemma that can be used. So as in Arnold's examples, I want to point out that one of the main geometric objects that we are going to use is a normally hyperbolic invariant manifold. And the standard shadowing lemma that applies for hyperbolic system does not work for normally hyperbolic invariant manifold. So the simplest example is you take a product system. So you can have in a product system as before. Think about Arnold's example without the perturbation. It's easy to create pseudo-orbits that move by some distance, but they do not correspond to true orbits in the system. So therefore, the shadowing lemma should have some extra conditions in the inner dynamics that allows for shadowing. So just to give a general picture of the Arnold diffusion problem, while the example proposed by Arnold was very special, he conjectured that the same type of result should hold generically for perturbations of integrable Hamiltonian systems of at more than 2 degrees of freedom. So namely, that there exist trajectories which visit a large fraction of the phase space, also symbolic dynamics. What do I mean by that? For example, if you have action angle coordinates, again, you want to find that there are trajectories for which the action coordinate changes by some quantity independent of the size of the perturbation. So, there is a standard classification for this problem due to Kierke and Galavotti. So there is the so-called a priori stable case when the unperturbed system can be expressed in action angle variables only. So there is no hyperbolicity in the unperturbed system to begin with. So this is like the harder problem. There is also the a priori unstable case when you already have some hyperbolicity in the unperturbed problem, so like in Arnold's example. And there is an even, let's say, simpler case, the a priori chaotic, not only that you have hyperbolicity, but you also have, for example, hyperbolic basic set. So essentially, this third case assumes that you already have in the hyperbolic system transverse intersection of the stable and unstable manifolds. And I will give concrete examples for each of these cases and some discussion about what has been done. So this is the a priori stable system. So you have an integrable system that only depends on the action variable, and you add a general perturbation. And for such system, resonances play an important role. And there are two formulations of the instability problem for such systems. So you consider the first order resonances. The first order resonances give you a codimension 1 surface in the action space, and it has been shown in the works of Bernard, Kaloshin, and Zhang, and also in works of Jean-Pierre Marcot, that you can associate to first order resonances some normally hyperbolic invariant cylinders. And for this, once you find transverse intersections of stable and unstable manifolds, and in principle, you can travel along these cylinders for a distance of order 1. So this is a weak form of diffusion because you are actually exploring just a small piece of the action space, so you are just moving along a single resonance. But more difficult question is this: what if you consider a dense family of single resonances, and you want to prove that there are orbits that follow these single resonances and move from one single resonance to another? So in that case, you have to construct a network of such cylinders, and at the double resonances, for example, if you are in 2 degrees of freedom, these cylinders are connected by singular cylinders, and then you basically move along each of these cylinders, but then you have to do some extra work in order to cross the double resonances. And there are very recent results in this area, and I would like to mention, first of all, the works of Kaloshin and Zhang, Cheng, and also by Jean-Pierre Marcot. So, and the point of this example related to this talk is that you have some normally hyperbolic invariant manifold, and you have transverse intersections of the stable and unstable manifolds. And I want to emphasize that for this general system, these geometric objects come after very, very hard work. But in the a priori unstable case, when you already have some hyperbolicity, you get these objects for free. So this is the case when you have, let's say, a rotator. Maybe instead of one pendulum, as in Arnold's example, you can put several penduli. And I'm going to put here some positive or negative signs in front of the Hamiltonian for each pendulum, just to emphasize that we do not need for our arguments a convex, positive, definite, unperturbed Hamiltonian as it is needed in a variational method. And we add a perturbation. So again, we are going to focus on the phase space of the rotator. So there are going to be some assumptions on the smoothness of the system. Also, we really want to say that each of these systems is really a pendulum. So it means that each potential has a unique non-degenerate global maximum for which it corresponds a homoclinic orbit. And then the perturbation here, we assume that it satisfies some non-degeneracy conditions that are verifiable, and they are also generic. So again, the point that I'm going to try to emphasize in this talk is that we are using the geometric method, and the geometric method has this feature that you can apply it to concrete systems. So you can take a system and check the hypothesis on the system, whether you expect or not diffusion. Moreover, the conditions that you impose on the system are going to be generic, and also the outcome of the geometric method is that when you obtain diffusing orbits, orbits that achieve diffusion, you obtain them in a constructive way, so you know exactly, or you have a lot of information about the trajectories, what they are doing. So it's a method that can be applied numerically or applied to concrete systems as well. So regarding the geometric methods, there are several papers that were showing this type of results with geometric tools, but of course there are variational tools and some other methods. And I should have said that from the very beginning. So there was a lot of work that was done in this area. So there are many, many references that unfortunately I'm not going to be able to list them all. So again, in this system, you separate in the unperturbed case the rotator part and the hyperbolic part. And if you fix your hyperbolic variables to the saddle point of the pendulum, then you are going to have a normally hyperbolic invariant manifold, and you have stable and unstable manifolds that you try to use to achieve diffusion. So again, this geometric object is very important. And the third model, which is for a priori chaotic system, so we start with a geodesic flow on some compact manifold, and we consider a Riemannian metric, but it can be a Finsler or Lorentz metric. And you want the Riemannian metric to satisfy some conditions that are generic. So namely that the geodesic flow on the unit tangent bundle should have a hyperbolic closed orbit, and the stable and unstable manifolds of these should intersect transversally. And the genericity of this condition for Riemannian metrics was proved by Gonzalo Contreras. So you start with a geodesic flow, you realize the geodesic flow as a Hamiltonian, where the Hamiltonian is really the kinetic energy, and then you add a perturbation. So the external perturbation is given by a flow on a torus, which has, so you have a motion with some frequency, and the components of the frequency are rationally independent, or in some of the older papers, there is this assumption that they are Diophantine. So this is your perturbator. So you have the geodesic flow, and you have a perturbator, and you have to couple them, and you couple them by the means of an external potential, and you create a time-dependent Hamiltonian. So this part here is just the geodesic flow. This is the, and to this you add the potential, and the potential achieves a coupling between the variable Q, which acts on the geodesic flow, and this is the external flow given by the quasi-periodic motion on the torus. And the diffusion translated into, for this system, is that there exist trajectories for which the energy grows to infinity over time. So if you go back, so in the original system, the unperturbed geodesic flow, in the Hamiltonian formulation, you are not able, the energy is preserved, so you are not able to grow the energy. So use the time-dependent perturbation, and then you can find trajectories for which the energy can grow as much as you want. Of course, that you can also find like symbolic dynamics, so you can prescribe the energy to go from one level to another in a prescribed manner. And again, so this is also a problem that it's called, I think it was first proposed by Mather, and sometimes it's referred as the Mather acceleration theorem, and there are lots of works that have been done in this area, including some people from the audience. So just what I want to say about this problem, it's again something very well known, that you have a normally hyperbolic invariant manifold if you do the proper analysis. So the assumptions on the metric was that you already have a closed geodesic that is hyperbolic, and by reparametrization you have such a geodesic at every energy level. Since you are trying to grow the energy, you put together all of the closed geodesic from some energy level and on, and this structure is a normally hyperbolic invariant manifold. And you also assume that the stable and unstable manifold of the closed geodesic intersect transversally. You put together all transverse intersection from some energy on, and you get a homoclinic manifold. So this is for the unperturbed system, and then you add the perturbation by the potential. So you work in the extended space, phase space. So now you have your, instead of your original cylinder, you are going to look at the cylinder times the external manifold, which is a torus. You introduce a small parameter, which is 1 over the square root of the energy. And if you do rescaling of the time and of the momentum, you write your Hamiltonian as a slow and small perturbation of the geodesic flow. So you have a normally hyperbolic invariant manifold for the unperturbed system, which survives for small perturbation. And again, you have some of the machinery that was present in the previous examples. So now, in conclusion, we looked at all of these examples, and we've seen some common features that we are going to try to explore. So namely, you have a normally hyperbolic invariant manifold. The dynamics restricted to that, it's nearly integrable. So you have some dynamics on it. You can express these dynamics in action angle coordinates. So the dynamics restricted to the normally hyperbolic manifold, I'm going to call it the inner dynamics. But another feature is that you have an outer dynamic, so you look at the motion along homoclinic orbits, and you have two types of dynamics for this system, inner dynamics and outer dynamics. So you can have pieces or segments of orbits for one dynamics and pieces of orbits for the other. It doesn't automatically mean that you can glue these together and get through orbits. So you need some sort of shadowing lemma to follow these segments of orbits. And this is what I mentioned before, that using this type of geometric approach, you can deal with concrete systems, so you can verify the conditions on the system, but also the outcome is explicit, so you have information on the diffusing orbits. So this is some background. So this is the well-known notion of normally hyperbolic invariant manifold, which means that you have a manifold which is invariant under the flow, and the normal direction is split into a stable and an unstable bundle, and the expansion and contraction rates along these bundles will dominate the expansion and contraction rates along the normally hyperbolic invariant manifold. And once you have this notion of a normally hyperbolic invariant manifold, it comes with a nice geometric structure. Basically, the stable and unstable manifolds are foliated by stable and unstable fibers of points. So the next ingredient that we are going to need in order to formulate some shadowing lemma is the so-called scattering map or homoclinic map. So this has been known for quite a while, but in terms of the symplectic properties, it was analyzed by Dersams, Deave, and Sara. So the idea is the following. So assume that you have a normally hyperbolic invariant manifold, and somewhere here is a homoclinic manifold. So for each point in the homoclinic manifold, there exists a unique stable fiber. So let's mark x minus the foot point of the, no, this is the unstable fiber. So x minus is the foot point of the unstable fiber. There is also a single stable fiber that goes through this point. So you mark by x plus the foot point of the stable fiber, and then in order to encode the dynamics by following the unstable manifold and then the stable manifold, you look at this map that takes x minus into x plus. So in order to have a well-defined map, you have to put some restrictions on the homoclinic intersection. You have to make sure that this is uniquely defined, and then it's a local diffeomorphism. So this is a map that is defined geometrically, so you essentially look at the stable and unstable fibers, but it is important to notice that what happens to the corresponding trajectories. So there is no trajectory that goes from x minus to x plus. So you have this map, so this map is defined on some domain in lambda in the normally hyperbolic invariant manifold and takes values in lambda as well. But there is no trajectory that goes precisely from x minus to x plus. So the map encodes some information about the homoclinic excursion, but it's not a true trajectory. So what is the trajectory doing? So if I look at the homoclinic intersection, and if I follow it backwards in time, so the backwards image of this point, of the homoclinic point, will asymptotically approach the backwards image of the foot point, and the forward image of this point will approach the forward image of the foot point. So essentially, the scattering map is something that you can compute easily, but then you have to translate the information given by the scattering map in terms of what the trajectories are doing. So if we live in the symplectic world, the symplectic map is also, the scattering map is also symplectic. So the main advantage of the scattering map, I mean the scattering map, if you just define it geometrically, it doesn't seem that spectacular, but the main advantage of this scattering map is that it can be easily computed, at least up to the first order, in a perturbative setting. So assume that you have a Hamiltonian system which comes as a perturbation of an integrable one, and assume that, well, maybe you have a normally hyperbolic invariant manifold in the unperturbed system, and this survives to some normally hyperbolic invariant manifold for all small enough perturbations. So, so for each epsilon, I'm going to get a normally hyperbolic invariant manifold that depends on that epsilon. So I'll have a system of coordinates on each of these. So in order to keep track of the dynamics on each of these manifolds, I'm able to parameterize each of these normally hyperbolic invariant manifolds in terms of the original one. So you do such a small parameterization and you have a reference manifold and you refer everything in terms of that one. So instead of looking at the scattering map on lambda epsilon, via this parameterization, I can look at the scattering map always defined on the unperturbed manifold. So I have a same manifold for all of these values of epsilon. So if you do an expansion of this scattering map in terms of epsilon, you are able to write something like this. So this is the unperturbed scattering map, and this is the linear part, which comes with epsilon coefficient, and this linear part, and then it's an error of order epsilon square, and the linear part, it's computable, so it's in terms of convergent integrals, and these convergent integrals mean, so one integral is for the forward dynamics and the other integral is for the backward dynamics, but each integral has two parts. One is to take the perturbation and compute it along a trajectory for the unperturbed system of the inner dynamics. So here you take a trajectory of the inner dynamics for the unperturbed system. And you have always another term, which is the perturbation acting of a homoclinic trajectory of the unperturbed system. So this part depends on evaluating the perturbation on trajectories of the unperturbed system, and there are two types of trajectories: trajectories of the inner dynamics and the trajectories of the homoclinic. And the advantage is that if you want to prove generically that the scattering map is making some growth, then you can perturb, you can do a small perturbation in a tubular neighborhood of a homoclinic manifold without affecting the inner dynamics. So it's very easy to do perturbations that make the scattering map non-trivial. So what do I mean by non-trivial? Let me look again at one of these very simple examples. When you have a rotator and a pendulum, when you compute the scattering map for this, the scattering map is the identity. But if you are willing to do a generic type of perturbation, again, you can create the result of such a generic perturbation is that the perturbed scattering map will increase the action variable. So essentially, you have a vector field here which describes the progress that is achieved by the scattering map, and if you make this vector field transverse to the action level sets of your system, then in this way you are able to increase the action coordinate. So the point is that the following. So if you are willing to assume, or if you pay the cost of a small perturbation, that this vector field is transverse to the level sets of the action variables, then you are able to grow by epsilon at each application of the scattering map. But the even more important point is that once you do a change in the perturbation so that your vector field that generates the scattering map is transverse to one action level sets, is actually transverse to an order 1 family of action level sets. So while the scattering map is always able to achieve a growth of only order epsilon, once you make a perturbation, you are able to move, at the end of the day, order 1 in terms of the action direction, if you are willing to repeat the scattering map over and over again. So now I'm going to formulate some shadowing lemmas for normally hyperbolic invariant manifolds. So first of all, I'm assuming always that I have a normally hyperbolic invariant manifold. I'm fixing a homoclinic manifold for which the scattering map sigma is well defined. And now let's suppose that I'm able to find a family of pseudo-orbits of the following type. So I start with one point in the normally hyperbolic invariant manifold in lambda. I apply the inner dynamics for a long enough time. I apply the scattering map, and then I apply the inner dynamics again. So provided that the inner dynamics is applied at each step for a sufficiently large amount of time, whenever I create such a pseudo-orbit, I'm always able to find a true orbit that follows it closely. So again, the idea is you start with one point, you apply the inner dynamics, scattering map, inner dynamics. And then you repeat, apply inner dynamics, scattering map, and inner dynamics. So each of these pieces of trajectory is not a true orbit, but then you are able to find a true orbit that follows it closely. So one question that you may wish to ask is that why do we have to apply the inner dynamics? Why not the scattering map? It's enough. So again, the idea is that the scattering map is geometrically defined, but the dynamical effect of applying the scattering map is you go from here to here, and then you follow the forward iterates by the inner dynamics, but also you follow the backwards iterates of the inner dynamics. So in order to use the scattering map to find true orbits, you have to have all of these parts of the motion: inner dynamics, scattering map, and inner dynamics again. So this is how we are creating the orbits, and the only condition is that the scattering map should be defined, should be applied for a long enough time. So what long enough means, so it depends on how close do you want to get with the shadowing orbits to the normally hyperbolic invariant manifold, but it also depends on the angle between the stable and unstable manifold. So the argument uses the lambda lemma and some topological methods based on correctly aligned windows, and the idea is that when you come close to the normally hyperbolic invariant manifold, you should come with a stable and unstable direction matching those close to lambda. So that's why if the angle between the stable and unstable manifolds at the homoclinic intersection is small, so you have to work hard in order to make that angle like straight. So one nice feature of this lemma is that if you have available some pieces of the inner dynamics created by some other methods, let's say by variational methods, so for example, if you have pieces of inner dynamics that follow elliptic islands or KM tori or Aubry-Mather sets, you can incorporate them in your construction. So you know something, you know some particular orbit for the inner dynamics that follows, let's say, an Aubry-Mather set, provided that you can jump with a scattering map in some other place, you are constructing, at the end of the day, a trajectory that follows closely the Aubry-Mather set, and then it jumps and does something else. So, of course, this is, in my opinion, a very useful lemma, but the other problem the problem that you have over here is that you have to first create the pseudo-orbit that is of this type. So the idea is, how can you create such an orbit? So, of course, I gave half of the answer. So if you know in detail the picture of the inner dynamics, you use the inner dynamics to create such a pseudo-orbit. But it turns out that you need very little information about the inner dynamics, and you are still able to construct this type of orbits. So the answer is you only need to use the recurrence property, and you are in a conservative system, so you can always appeal to the Poincaré recurrence theorem. So let me just read what this lemma says. So assume that you create an orbit just by applying the scattering map over and over again. So you apply the scattering map once, you land at some point, you apply the scattering map again and again and again. Now assume that you have some recurrence in the system. So maybe your lambda is compact, and then you can apply the Poincaré recurrence theorem for the inner dynamics. Or if it's not compact, maybe each point of this orbit of the scattering map has a neighborhood restricted to which the dynamics is recurrent. So this formulation is a little bit awkward, but to make it simple, assume that you are in a compact, normally hyperbolic invariant manifold, and you apply the scattering map over and over again. So you have the Poincaré recurrence theorem that tells you that after you apply the scattering map once, then you can use the inner dynamics and come back to that point. So why do we need to do that? I mean, we are trying to appeal to the previous lemma. So in order to obtain the shadowing orbits, you need to have not only the scattering map, but also some pieces of the inner dynamics for a long time, and use the recurrence to create this piecing of the inner dynamics. So essentially, you apply the scattering map once, and you land in some neighborhood, and almost every point will return to that neighborhood. So, and you can always return after time as long as you wish, and use those points whose return time is very long to jump again, and then you use the return time, and so on. So out of an orbit of the scattering map, actually out of a pseudo-orbit of the scattering map, you are creating another pseudo-orbit which consists of applying the scattering map, apply the inner dynamics for a long enough time, apply the scattering map, apply the inner dynamics for a long enough time. So we are going back to the previous lemma. There is a true trajectory that follows these pieces. What do you lose here? You lose control. So once you are willing to appeal to the Poincaré recurrence theorem, you are not going to know how long of a time it takes to come back here, and what is this trajectory doing. So now this is a general diffusion result that essentially can be applied in all the examples that were mentioned at the beginning of the talk. So assume that you have a perturbed Hamiltonian, and that for all epsilon sufficiently small, you have a normally hyperbolic invariant manifold. You have this scattering map, which is described by the expansion. This is the Hamiltonian that generates the scattering map up to order 1. And assume that the unperturbed scattering map is of this form. So this can be the identity, for example, which is the case for the pendulum rotator system, or it can be a shift by some fixed angle, which turns out to be the case for the geodesic flow. Or it can be a shift by an angle that keeps changing, which is the case for some examples from celestial mechanics as the elliptic three-body problem. So if you know that the vector field that generates the scattering map is transverse to some level set of the action variable, then for all sufficiently small perturbation, you are able to find trajectories for which the action variable changes by some quantity independent of the size of the perturbation. So what I want to point out is that you really don't need to have any information about the inner dynamics, about the dynamics restricted to the normally hyperbolic invariant manifold. I mean, one of the standard assumptions that is used in many papers is that the inner dynamics is a twist map. You don't care about that. It doesn't have to be a twist map. So all you need is the conservative property of the inner dynamics. So, and the argument in a couple of lines is the following. So if you have this vector field, which is transverse to one action level set, so the vector field itself does not depend on epsilon. Let me go back to this expression. So the vector field that generates the scattering map does not depend on the size epsilon of the perturbation. So once you create such a vector field that is transverse to one level set, is transverse to an order 1 family of level sets of the action, so then you apply the scattering map 1 over epsilon times, you are able to travel order 1 in the action direction. And essentially use the recurrence to do what I mentioned before. So once you apply the scattering map, you want to come back and jump again. So you use the Poincaré recurrence theorem to do that. Since in some examples we don't have a normally hyperbolic invariant manifold which is compact, so we have the following dichotomy. So you use just the inner dynamics, so you start with a order 1 piece of the normally hyperbolic invariant manifold, and you apply the inner dynamics forever. Do you escape? If you do escape, then you have diffusion without using the outer dynamics. You just escape by the inner dynamics. If you do not escape, if you stay confined to some compact region, then you apply the Poincaré recurrence theorem and use the previous lemma. So now let me just illustrate this method on a couple of examples. So I'm revisiting the example considered in Del Sams, de Avanzara, when I have a pendulum, rotator, and a small periodic coupling. So I have all of those geometric objects described before. There is one less requirement in this statement, namely you do not require that the dynamics restricted to the normally hyperbolic manifold, it's a twist map. So you do not require the positive definiteness of the rotator part of the dynamics. So even though you are able to prove that there exist trajectories that achieve diffusion. So in the previous work of Del Sams de Avanzara, they did require this non-degeneracy condition that translates into the existence of KM tori, elliptic islands, and so on. So here, once you do not make this assumption, the geometry can be quite complicated. So there are some papers by Green and collaborators that look at non-twist maps, and there are some regions for the non-twist maps where you cannot apply Aubry-Mather theory and so on. So there are these type of structures that are not completely well understood. We can still apply our diffusion result even if the inner dynamics is of this kind. So let me say something more about this statement. If we do not use the positive definiteness of the rotator part, we do obtain diffusion, but with no extra information on the dynamics. So just to prove this theorem, we are going to use the Poincaré recurrence theorem type of argument, which gives no quantitative information beforehand about how long it takes for orbits to return. So the time here can be very long. But if you are willing to assume that the inner dynamics is essentially a twist map, you can actually prove that we can achieve diffusion in the time which is of order 1 over epsilon ln of 1 over epsilon. This time has been conjectured as optimal by Loschak. So the point is that well, this is a page full of formulas, but what do they mean? You can you start with your system, and the unperturbed system has the stable and unstable manifolds coinciding. So you apply Melnikov theory to say that generically you are going to get a splitting, and then you measure that splitting, but by measuring that splitting you compute explicitly for that particular example the scattering map up to the first order. So the scattering map is the unperturbed part, which is the identity, and then you have the first order part, which is epsilon times a vector field, and you can arrange this vector field to be transverse to the action coordinate via choosing the generic perturbation O1. So then you are exactly in the setting of the previous lemma, and you achieve diffusion. So if you want to achieve diffusion with optimal time, you need more information. You need to make sure that you are traveling fast enough by the inner dynamics, so you need to use some averaging. So in order to use some averaging, you have to make this extra assumption that the inner dynamics is like a twist map. You use first order averaging. So you have this strip, which is created by the Hamiltonian that generates the scattering map. If you are, so essentially, you have a picture in action angled coordinates. So somewhere here, you have a region where this is transverse to the action level set. So this is a piece of order 1 size. So it's order 1 in the I direction, but it's also order 1 in the angle direction. So if you are here, the scattering map will always grow, but this is big enough, so whenever you start, and if you want to come back, you don't really have to come back to the original point. You can come back to any point on this strip. So use the averaging to go as fast as you can and land on some piece of the strip. Use the scattering map, use the inner dynamics, and so on. So using averaging, you are making sure essentially that what you gain in terms of the action variable in one step of the scattering map, you are not losing when you apply the inner dynamics. So your net change is going to be order epsilon, and it takes an order of ln of 1 over epsilon to follow this scattering map. So basically, you just do a simple arithmetic and you figure out that you achieve optimal diffusion time. So, and the other example is we are going to revisit the perturbed geodesic flow, and what we are going to learn from this example is that, again, you need much fewer restrictions on the type of the perturbation that you can apply. So the setting, the original setting for the unperturbed system is the same, so you have a geodesic flow on a compact manifold with a generic metric. But in the previous example, the perturbation was quasi-periodic, so it was given by a rotation on a torus. In our case, we can afford more or less very general type of perturbation as long as it satisfies some mild recurrence. So essentially, instead of having this quasi-periodic motion of a torus, we take any compact manifold with a flow on it, generated, let's say, by some vector field, and the only assumption is that this flow, whatever it is, has at least one uniformly recurrent point. So what is a uniformly recurrent point? So this is a recurrent point with bounded time. So if you look at a time interval which is long enough, you are always going to be able to return to the original point within that time interval. So now you have the same type of coupling of the geodesic flow with this perturbator by a potential, and you create this time-dependent Hamiltonian. This is the unperturbed geodesic flow. This is the potential that couples the motion of the geodesic flow with this flow on an external manifold. And again, the only restriction here is that you have a uniformly recurrent point that is non-trivial. I should have mentioned that you have this condition, you have a non-trivial. Well, this is a very general type of system because on a compact manifold you always have uniformly recurrent points. And again, it follows from Poincare recurrence. But the only ingredient is you should be able to find such a uniformly recurrent point that is not a fixed point for the flow. So if you find something like this, you can use it to replicate the Mather acceleration theorem. So there are trajectories for which the energy of the perturbed system grows to infinity in time. Moreover, we are able to prove that there are such trajectories for which the energy grows at a linear rate, and this is optimal. So you cannot beat linear rate. So how do we do that? Again, we follow exactly the same patterns as in the previous example. So we construct pseudo-orbits. So a pseudo-orbit will essentially be one application of a scattering map plus one segment of the inner dynamics. So you take such a elementary pseudo-orbit and you do some computation in terms of convergent integrals. So it's to measure the change of energy along such elementary pseudo-orbit. And you find that it's, for the system, you grow epsilon cubed times some factor. So again, this is given by integrals of V, the potential, evaluated along some segments of homoclinics and along some segments of the trajectory of the geodesic. So if you want this to be non-trivial, you make sure that you apply a small perturbation, you localize this small perturbation in a tubular neighborhood of the homoclinic, you are not affecting the inner dynamics, and then you create this quantity to be non-trivial. So then, every time you follow the scattering map and the inner dynamics for some time, you are going to grow consistently epsilon cubed. So, well, there is another trick that you need to involve. So, typically, if you have one homoclinic, you have infinitely many. You choose two distinct homoclinics, and generically, one of them will allow you to grow energy more than the other, because if they grow exactly the same, you just change one of them a little bit, and they are not going to have the same contribution to the energy at the same time. So, to make a long story short, you have two available homoclinics. One grows more energy. So you use the one which grows more energy when you are in the right spot to jump, when you are in the bad spot to jump, when you are in the location that you cannot apply the convenient scattering map. You use the other homoclinic, the less advantageous one. So one grows energy, one does some energy change that is subdominant. So on average, you keep growing the energy at the rate of epsilon cube per elementary pseudo-orbit. So you choose your elementary pseudo-orbits, you call the previous lemma, and there is a true orbit that follows them. So of course that there is some analysis in the background that I'm omitting, so you really use that analysis in order to construct these pseudo-orbits carefully and to achieve the linear growth in time. And I'm going to stop here, and thank you for your attention.